Hi, time for a short discussion about the properties of alkenes and alkynes by being very similar to each other. This isn't very complex, but it's worth a few moments conversation. The alkenes and alkynes are very similar to alkanes in the sense that they're all hydrocarbons. That means with only carbon and hydrogen as their components, the carbon and hydrogen bonds are not polar, and therefore the compounds themselves are described as nonpolar. So when they only contain nonpolar bonds, that's all you get. So that means they're not polar because the atoms, carbon and hydrogen, have essentially no significant difference in their electronegativities, if you remember that concept from a previous course. The result is that these compounds then are not like water, and so therefore they are not going to dissolve in water. They're insoluble because like dissolves like, and water is polar. Instead, they'll be soluble in these things that we call nonpolar compounds, organic compounds, things like, you'll hear about them later, but there will be ethers, there will be other alkanes, there will be other petroleum-based products, and you'll see them later in lab. All of these hydrocarbons are generally going to be described as having densities of less than 1. The density of water, which is therefore 1, means that these things are all going to float on top of a water layer. Think about what you've done or will be soon doing in lab. Because these molecules have only carbon and hydrogen in them, there are no polar bonds, there are no other intermolecular forces, and so all they have is London forces. And of course, yes, you should be reading this in your textbook. So as the molecular weight increases, the number of electrons increases, and therefore the London forces will increase as the molecular weight increases, which is the explanation for why two compounds that are quite nonpolar and very simple, like nitrogen and helium, have quite drastically different boiling points. Helium is crazy cold at 11 Kelvin, and nitrogen is still very cold, but considerably higher at 77 Kelvin, and that's because liquid nitrogen is a larger molecule, still not polar, much smaller than the atomic helium, and it gives a higher boiling point. The more electrons in the compound, the higher the boiling point, even when there's nothing else, especially when there's nothing else to consider. The other influence that can be noted is that, and this one is more interestingly not challenging, is that the London forces are going to decrease for a more spherical molecule. That gives you differences in boiling points based on shape. So shape matters when you have very similar compounds. Here's two examples. The compound on the right is simple ordinary pentane in its straight chain form. Oops, sorry. And I was trying to make the Java go away. And the straight chain form of pentane has a boiling point shown there at 35 Celsius. If you compare that, recalling that this is C5H12, to the compound on the left, C5H, well, keep looking, dimethylpropane, it's got 3 hydrogens on carbons on 4 sides. That's C5H12. These two compounds are isomers. Okay, they're very similar, but they're not the same. They have unique names. They also have highly unique boiling points. And the lower boiling point is going to be observed for the compound that has a more clustered or spherical or whatever, less stretched out shape. So the shape does matter for similar compounds with identical components but different shapes. Not always examples show up here but on this, but once in a while they do. So in other respects, the alkenes and alkynes, compounds that are unsaturated, are going to be much like the other hydrocarbons we began with, namely alkanes, in terms of melting points and boiling points and various other physical properties. Overall, much similarity. So the boiling points increase with increasing molecular weight, and they're directly related to the amount of London dispersion forces. We'll keep talking about these more with time. These also increase with increasing molecular weights. So the boiling point increase as the molecular weight increases. And as shown on the previous slide, for hydrocarbons with the same molecular weight, the boiling points will decrease with increasing amounts of branching or clustered structures. And those were the pictures shown on the previous slide. The other thing to remember is the chart we began with in chapter 12, relating the number of carbons to the temperatures of the melting and boiling points. And they always increase with the number of carbons because it's right back to London forces and how the molecular weight increase gives you increases in molecular forces, and that gives you a higher melting point or a boiling point, either one. There you go. So they are going to be, alkanes are gases for carbons less than 4. Alkenes, we won't make that hard and fast generalization, but there will be a point beyond which they're always liquids, and or eventually they could be solids. All right, the other two other notable pieces to describe about alkenes is, of course, that they have cis and trans isomers. And remember that cis is going to be different from the trans in how the substituents are arranged around the double bond. These compounds will sometimes have slightly different properties, sometimes noticeably different. And in biomolecules, they can be drastically different in interesting ways. But we won't come into all those examples all at once. They'll come up gradually. As is the case for every other hydrocarbon, these compounds are also flammable. Oh yes, surprise, surprise. Do not put matches near these things unawares. And if they're gases, they tend to be less than toxic, interestingly enough, but not something you want to indulge in when you're not sure. The last piece that is key here, though, is that these unsaturated compounds are going to be chemically reactive because of the double bonds. And the reaction type that is exhibited most of the time is the addition reaction. So a compound is going to be adding something to make two parts to make a third component. And we'll see examples of those reactions in this chapter. All right, not a long discussion, but those are worthy things to notice about the properties of alkenes. I hope that helps you on your homework. And as you study, keep asking lots of questions, and I'll see you in class.